Do you actually have free will? Did you consciously choose to click on this video today, or was that decision locked into place 13.8 billion years ago at the exact moment of the Big Bang? For centuries, the brightest scientific minds leaned heavily toward the latter. When Isaac Newton published his laws of motion, he gave humanity a mathematical blueprint of reality. If you knew where an object was and how fast it was moving, Newton's equations could tell you exactly where it would be tomorrow, next year, or 1,000 years from now. The physical world suddenly made sense. Using these rules, astronomers could look up at the sky and pinpoint the exact minute and location a solar eclipse would shadow the Earth, decades before it actually happened. This incredible predictive power led a French mathematician named Pierre-Simon Laplace to propose a thought experiment in 1814. Imagine a super intellect, later known as Laplace's demon. If this intellect knew the precise location and momentum of every single atom in the universe right now, it could calculate the entirety of the future and the past. Under this strict Newtonian view, the universe operates exactly like a perfect, reliable clock. If every cause has a perfectly calculable effect, then the future isn't a blank page. It is a book that has already been written in full, and we are simply turning the pages, acting out a sequence of events predetermined by the initial state of the cosmos. But that perfect clockwork dream contained a mathematical flaw, one that frustrated even Isaac Newton himself. If you have two celestial objects in an empty void, say a star and a single planet, their gravity locks them into a neat, predictable orbit. You can calculate their exact positions thousands of years into the future. Add just one more star to that system, however, and the math falls apart. In a three-body problem, all three bodies are constantly pulling on one another. Star A moves, which changes the gravitational pull on star B, which alters the path of star C, which violently yanks back on star A. It becomes an infinitely complex, chaotic tug-of-war. For over 2 centuries, brilliant mathematicians tried to find an equation to solve this. But in the late 1880s, Henri Poincaré proved that they weren't failing because they lacked intelligence. They were failing because there is no clean mathematical formula to predict a three-body system. We see the consequences of this math in our own stellar neighborhood. Alpha Centauri is a genuine 3-star system where any theoretical planet would face a nightmare of instability. You might live through years of temperate calm, only to be thrown into ocean-boiling heat or a deep freeze with zero warning. Even though every single star in that system perfectly obeys Newton's laws of gravity, their collective future remains entirely unpredictable. The rules are absolute, yet the outcome cannot be calculated. We don't even need to look to distant star systems to see this breakdown. In 1961, at MIT, a meteorologist named Edward Lorenz was using early, rudimentary computers to run mathematical weather models, plugging in variables like temperature, air pressure, and wind speed. One day, wanting to save time, Lorenz restarted a simulation from the middle instead of the beginning. He typed in a number from his previous printout, 0.506, but the computer's memory had actually stored the number to 6 decimal places, 0.506127. He had shaved off an amount roughly equivalent to 1 part in 5,000. This chart shows exactly what happens when you alter a complex simulation by a fraction of a fraction. The two weather patterns tracked identically for a brief moment, but soon they rapidly diverged into completely unrelated climates. A microscopic rounding error meant the difference between a sunny day and a massive storm system. Lorenz had stumbled onto what we now call the butterfly effect. Weather is incredibly sensitive to initial conditions. A tiny disturbance in the air, like a butterfly flapping its wings in Brazil, can compound and interact with other atmospheric layers until weeks later it helps spawn a tornado in Texas. To perfectly predict the weather a month from now, we would need to know the precise temperature and pressure of every inch of the globe at this exact second. Because human beings will never have instruments capable of measuring a system with infinite precision, the long-term forecast of Earth's atmosphere will always slip through our fingers. Both the three-body problem and the butterfly effect rely on our inability to measure complex systems. that if we zoom past the macro world of weather and gravity down into the quantum realm of isolated subatomic particles, we hit a hard physical limit to predictability itself. In the 1920s, Werner Heisenberg formulated his famous uncertainty principle, a concept so deeply strange it disturbed the founders of quantum mechanics. Heisenberg's principle states that you cannot simultaneously know both the exact position and the exact momentum of a particle like an electron. If you measure precisely where the electron is right now, its speed and direction become totally blurred. If you measure how fast it's going, you lose track of where it is. This is the final nail in the coffin for Laplace's demon. The demon requires flawless, absolute knowledge of every particle's position and momentum right now to calculate tomorrow. But quantum mechanics strictly forbids those exact initial conditions from even existing at the same time. We aren't failing to predict the quantum future because our microscopes are too weak. We are failing because deep unpredictability is baked directly into the foundational fabric of reality. So, if the universe isn't a predictable clockwork machine, what is it? A chaotic random mess where anything can happen at any time? Actually, no. When Lorenz graphed chaotic weather data, the points didn't scatter randomly. They traced a highly organized shape, a strange attractor. The short-term path is completely chaotic, never crossing its previous track. Yet long-term, it remains confined within a stable boundary. This phenomenon reveals a hidden order beneath chaotic systems, which shows up in the physical world as fractals. In fact, nature uses these self-replicating patterns absolutely everywhere. The branching of your lungs mirrors a sprawling river delta, a jagged snowflake, and the cosmic web of galaxies. This represents the magnificent middle ground of the cosmos. Reality follows strict rules while maintaining deep unpredictability, allowing for complex hidden orders to emerge from the noise. This delicate balance between order and chaos scales all the way up from atoms and weather systems directly into our own daily lives. Human lives are incredibly hypersensitive to initial conditions. A minor choice, taking a different route to work or speaking to a stranger, compounds over decades to shift the trajectory of an entire life. Our predictive power hits a wall, not because of weak technology, but because the universe provides the literal room for free will to exist. Whether we are looking at the gravitational pull of distant stars or the vibration of an electron, the cosmos actively refuses to be a predictable machine. The universe is an open, unwritten book, leaving our lives full of genuine surprise, absolute freedom, and boundless possibility.